Generative AI, so many trends. Dealing with fast-paced open innovation is something that I wanted to discuss today because I think this is very important sometimes to step back and look at the number of dimensions of a problem, the number of trends, in order to understand that agility is going to be super important in a fast evolving world of innovation for generative AI. So you might have seen this video that I posted recently that is trying to discuss about the classic machine learning paradigm as opposed to generative AI and discuss what has really changed. One dimension that I'd like to focus on today is about the number of dimensions. What do I mean by the number of dimensions? Well, if I show you this simple well, it's not really simple, by the way, but this diagram of a typical architecture using an LLM in order to solve some tasks, in this case related to networking. If you look at the flow, let's have a look, for a few minutes at what it looks like. So basically, you have a user, you want to ask a question to your system and say, show me if there are any correlation between the quality of experience of a given application and the delay along the path to reach out to this application hosted somewhere in the cloud. Suppose that this is a question you want to ask. In this case, you would interact with an agent. This agent would have the ability to access a knowledge database, what is sometimes referred to as long-term memory. And of course, you can store in this database some documentations, you can store some recipes in kind of cookbook, history of what worked in the past. And what you would do is that the agent would have to retrieve on the fly the relevant information. This is the RAG, then build a prompt. And in the prompt, you can have a lot of things, general instruction, you can have reasoning instruction, you can, of course, have what you have retrieved thanks to the RAG. And then you will interact with one or multiple models. Some of them may be large, other ones may be smaller and specialized. They may be interacting with each other if you have a multi-agent system. And as you can see, if you step back a little bit and you compare with a classic machine learning problem, like a regression problem, where you know that you have some parameters that we usually call hyperparameters that you may have to tweak. You may have even, you may want to use some system that will automatically do a grid search or with different approach on how to tweak these hyperparameters. But look at that system you have in front of you. You would have to look at all of these dimensions together, decide about the training strategy for your model, decide about the best prompting strategy and how to tweak it, design the RAG methodologies, the embeddings, and so on and so forth. So this is what I wanted to share with you and have a look at what's going on in the world of generative AI these days. And of course, we are engineers, we love technologies. I would never complain about the pace of innovation. I think this is a good thing. But at the same time, we need to be aware of it, step back, look at the big picture, and maybe be able to adjust ourselves in terms of agility, especially when you build high quality systems using generative AI. So let's have a quick look now. Racing towards larger models. And that was a very famous race up to, that started at the very beginning when people said, okay, I've got 10 billion, 70 billion, 150 billion, you name it, right? The number is not very important, but there was a real belief that the larger the model, the better. And of course, if you have a large model, you need to have a large amount of training data, what we call the tokens. The Chinchilla laws says that it should be about 25 more than the number of parameters. It's a rule of thumb, obviously. So we started to see this kind of trend with very large models, a lot of data, and the bigger the better. Okay. Then, we looked at the quality of the data. And I think that the work being done by Microsoft, especially around Phi model, which is a fairly small model. We're talking about a bit more than 3 billion with Phi 2.0 is super interesting because in this case, they need less data, but they try to focus on the quality of the data. And that's why they call it a textbook, all you need, referencing the famous attention is all you need. But this is very important because in this case, that could be another trend where you may want to use smaller models with higher quality of data as opposed to a big model with a huge amount of data for which it's harder, of course, to control the quality, or at least you may even have, by the way, some strategies when you can decide the percentage dynamically, the split between the real data, synthetic data, and the different type of qualities. So there are many ways to do that. So prompt engineering, what an important dimension. There are many ways to do prompt engineering. You can use chain of thought when you ask the model to explain the steps, if you will, and we see that it does help dramatically. In-context learning has been used from day one when you may want to provide some examples. Sometimes none of them, zero-shot learning, sometimes one-shot, two-shot, three-shot learning, and you see that it does help as well. Look at the size of the context window. We started off with a few thousands of tokens. Then we started to see a few models with 100,000 tokens. Now we see Gemini 1.5 with 1 million tokens. There are different choices to make. In some cases, it seems that the bigger the context may not translate to better efficiency because some data may be lost in between. So there are multiple approaches with pros and cons. There are multiple agent strategies like the tree of thought, which I believe is also very interesting when basically you have an agent that is moving in the sort of a tree, evaluate how promising is a given path, and then maybe crank back and do this sort of thing. So you can also have different strategies if you have access to the decoding loop and do some beam search. Anyway, I could go on and discuss about the prompt strategy, but as you can see, in this dimension, you can have a lot of things to tweak. Knowledge distillation has been very interesting also. The idea is to have a master model of very large size that could be used to train a smaller model. And then you would distillate, if you will, the knowledge between the two with the hope that the small model would be good enough at some point without the cost of inference of a large model. I won't talk too much about multi-model models like Gemini or GPT Vision. The idea in this case is to say, why stopping at the text? We're using already a big chunk of text. Maybe we can start using videos as well and sound. And maybe the output is going to be also in the form of video and sound. And, there are multiple ways to combine all of that and have a better representation of the data. Maybe that could help also to build world-based models and things like that. So this is yet another dimension when you decide about what should be the best design for your system. You may want to go for multimodality, basically. So interpretability, fascinating topic. Do we really need to be able to interpret a model? If you look at the brain, that's not something humans are really good at because they have not been pushed in this direction, if you look at evolution. So is it a requirement to interpret how the model works as long as you can look at the fairness, and there are multiple approaches to do that as well? There are hopes, I would say, but if you look at a simple decision tree that you can use for classification with machine learning, that's very, very easy. You can easily interpret and see what's going on. If you look at a deep neural net, this is way harder. If you now look at a transformer and a GenAI infrastructure, when you have a lot of components interacting with each other, this is even harder. So some people, they look at approaches to look at activation patterns and things like that. Mechanistic interpretability is very interesting. Monosemanticity, when you're not looking at a single neuron, but a pattern of activation of neuron, which has been confirmed by neuroscience, by the way. We've known that for a long time. These are very interesting topics. but that's something you need to look at as well. This is a dimension that needs to be taken into account. What is the requirement for you to be able to do some interpretability, if you will? Sometimes by regulation, we have to do that. It's not always the case, but that's a very interesting dimension for sure. Large generic models compared to small fine-tuned models. It's a super interesting topic. It's not very obvious. And if you look at some experimentations that have been done lately in healthcare, we could see, for example, that using a very large model would be as good as using a fine-tuned model with a very specialized data set, where you may not expect that, but in terms of cognitive capabilities, apparently the small models was missing a bit of that. It's not to draw any conclusion, because it may not be true with another use case, and even in the use case of healthcare, this may be wrong tomorrow. But this is important to think about it when you design your system. That's another dimension. How do I want my system to look like? Do I want to decompose the tasks and share the load between multiple models, one of them being large and responsible for planning, for example, other ones being more specialized to write code, for example? There are different approaches. Synthetic data generation is very, very interesting. What we used to do in the past with classic machine learning, and we are still doing, by the way, is look at the data set, do some cleanup of the data, but it was very rare to start generating synthetic data. And I've always been very prudent on my side doing that. But we do see now that when you mix real life data and synthetic data, for which you can control the number of biases, by the way, which is really cool. You can also control the quality a bit more. Then in this case, you may define the mix between the two. In some cases, we've seen models like Orca 2. You can achieve really, really good efficiency of a system using synthetic data. This is yet another dimension. What kind of data do I want to use to do the training? There are many new AI paradigms that I would love to investigate much more. I will probably post a video on the bio-inspired, because this is a topic very close to my heart, and discuss about the number of approaches writing software that may be more inspired by the human brain. As you know, the human brain is about 25 watts with 85 billion neurons and as many glia cells that we always forget, by the way, but it's a different topic. And how is it that we can achieve so amazing tasks with only 25 watts of power? Some companies, they started to look at different kind of software design, so we can run transformers on the CPU, which is also very interesting. There might be new ways to look at what a biological neuron can do in terms of a complex computation, which is far from the very simple models we're using for digital neuron. I won't talk too much about organoid intelligence, but this is a more research area, but very interesting for sure. And there are new learning paradigms as well for world-based models. Personally, I think that we're going to see more and more reinforcement learning being used in combination with other approaches, and the science of learning is also improving quite a bit. And there are other ones as well, like the one from Meta that I wanted to mention. Training strategies. There are many ways to do the training. You may want, of course, for alignment to use RLHF, RLAIF as well, or maybe DPO if you want to. This is important. It may be at the cost of the quality of the answer sometimes. We need to bear that in mind if you want to have an answer that is more aligned. And there are ways, by the way, to use RL technique, by the way, to find the best compromise. Process supervised reward is a very interesting aspect of it. Grokking. Why is it that if you start training for a long time, at some point you seem to see some kind of generalization? I would be very prudent when talking about generalizations for sure, because it's a holy grail we all want when we look at learning. But this is an interesting aspect of it. So maybe it might be more of a time spent in training than just the volume of the data, and then we know that there is a compromise. Curriculum learning is also very interesting. The strategy might be to start with a simple problem, and then you increase the complexity of a problem, and with such a strategy, you come up with a more efficient outcome. So as you can see, there are many strategies for training as well. Knowledge database, we've been talking about that for some time now. How do you want to design the embeddings, for example? You have choices between multiple embeddings. We start to see more embeddings coming up with different type of dimensions, ways to compute the distances. This is super important. You might have heard of CLIP as well and some cross-model embeddings. You may, in some cases, want to backprop and fine-tune the embeddings so that you can optimize the system. But this is a very important dimension of a space, if you will, that has to be tuned and looked at because it will influence the performance. When you talk about the RAG, there are also many possibilities to retrieve the data that you want to input in your prompt. If you haven't looked at that, look at Retro Plus. There are multiple ones like that, but this is the way you do the intention, if you will. So a very promising way of doing the RAG as well. And of course, we see so many progress in terms of next generation compute with new generation of GPUs, TPUs, DPUs, you name it, AI accelerators, and use of CPUs as well to do the inference, which is a very interesting aspect. The network keep improving. A topic obviously close to my heart. We're designing next generation networks that can be used in order to train your models and do the inference that have the amazing capabilities in terms of zero loss, which we know is very important. And think about it, the GPUs are getting so powerful that in some cases, they keep waiting, which is not something that you want. And so the efficacy of the system is extremely important. Look at all the work around Rocky and RDMA and all these things, but these next-gen networks are highly capable. So this is super, super important to look at that. There are multiple techniques to do dynamic compute optimization. Look at confidential computing, which is also very interesting because in this case, you don't have to worry at all about exposing your data in the cloud. Of course, it's not to say that this is the only technique by far, but this is a very interesting trend for sure. Agent strategies, I talked a bit about trio thoughts, the React framework, multiple agents collaborating. I'm a strong believer in multi-agent architectures. This is, in my opinion, a very promising path ahead of us, but this is also another dimension. It's no longer a single algorithm for a single problem. You may have now multiple agents, each of them using different kind of algorithms as well that work together. Mixture of experts, super promising. We see results already with Mixtral, with other big models that are using it. This is the idea of using lighter, more specialized kind of models that are experts and work together, but this is only a subset. So this is an improvement in terms of efficacy, if you will, and speed. And there are many, many aspects that are super interesting. And of course, I'm not going to cover all of the optimization techniques, such as the efficient memory management aspects of it, the way to do the inference with continuous batching, speculative decoding, very interesting as well. There are many, many aspects there that I don't want to cover, but if you look at your overall system, you will at some point have to look at this dimension of the issue, which is how do I optimize the training? How do I optimize the inference cost? Because there is still a challenge, I would say, in terms of power consumption. So this is yet another dimension. So how can we conclude? Well, I think the best way to conclude, when you step back a little bit and you look at the complexity of the system, the number of components that are intertwined and have dependency between each other, you really need to say, okay, first of all, we need to be very agile. And my recommendation would be, don't focus too much on a single component. Make sure that your metric is not focusing only on a single component, because maybe tomorrow that component will be gone or maybe upgraded or will change, and you will have to rethink the entire system. And I think that it is even more important than before to have a very strong evaluation platform that can basically look at the efficacy of each of the component, and especially the efficacy of the whole system with some instrumentation, so that you can avoid to do too many trial and errors. Because when you do a proof of concept, this is not an issue. You can afford to do that. When you are developing a very large and complex system deployed at scale, you can't afford to do that. So you need to have that. Have a look at that blog if you haven't done so yet. I'm discussing about the relevant metrics for AI systems, and especially generative AI, that could be of interest to you. Bottom line, we have a lot of technologies, we have a lot of trends. I think it's important to step back, make sure that you understand how they interact with each other, because we are building a system at the end of the day. And so have a strong evaluation platform as well is very important, and stay very much agile. I think this is really the bottom line. Thank you very much for your attention. Don't hesitate to reach out to me if you have any comments, any feedback, any recommendation on what you'd like me to discuss next time. Thank you.